Hi all, my name is McAuliffe. I'm a postdoctoral research scientist based at Rothamsted Research, and today I'm going to discuss carbon footprints and livestock, our current methods, the real challenge. So back in 2018, a seminal piece of work was published, which essentially became an encyclopedia or a bible of environmental footprints of all major agri-food products. And this new global encyclopedia of sustainability assessments suggests that meat is bad and plants are good. There doesn't seem to be much grey area in between. But despite the study's apparent robustness, it fails to adequately assess a number of critically important factors related to agri-food systems. These include intra-farm complexities. So if you think of how even on a single individual farm, different animals may perform differently to others, which would affect the carbon footprint of those animals or the products that they produce. Unrealistic or worst case scenario land use change assumptions. So by this we mean assuming that all the soy being consumed by livestock in the studies under consideration are coming from deforested areas of South America. Despite the study claiming to use nutritional indicators or functional unit, which we'll elaborate on a bit further on the next slide, there's actually no consideration of important nutrients such as vitamins and minerals. The only nutrient examined is protein. And finally, this protein content is poorly justified amongst individual food items, and there's absolutely no acknowledgement of protein quality. So just to sum up on this study, it's a very large database of very useful information, but there are a lot of methodological weaknesses which the carbon footprint or sustainability assessment community um, are working quite actively on improving. So I used the term functional unit in the previous slide, and it's worth spending a minute on the term. The term comes from life cycle assessment, or you might be more familiar with the term carbon footprint, which falls under the life cycle assessment umbrella. And essentially, a functional unit is a scaling factor which all emissions of a given system, so take for example, if you wanted to compare uplands, lowlands, and hill sheep production in Wales, you might want to use a functional unit of 1 kg carcass weight or 1 kg live weight to standardize the emissions so that you can compare them quite easily. So you would be comparing all emissions as 1 kg of carcass weight or live weight or whatever it might be. But there's a big problem when it comes to agri-food products of using these simple mass-based or in the case of dairy systems, volume-based functional units or output denominators. And the major problem with this is that they don't account for differences in nutritional quality, and the term functional unit denotes in itself that the unit being used should be determined by the function of that system, and we would argue that the function of agri-food systems is to produce nutrition. So what we're going to look at today is how some nutritional indicators have been used in life cycle assessments, and as you can see from the bottom of the screen, quite a few studies have been published, and the number is growing exponentially every year on developing new indicators on how to better account for the fact that food is consumed as a source of nutrition rather than simply being an output from a farm as mass or volume. Another avenue for connect accounting for nutritional quality in LCA is to calculate nutritional density scores for individual products. The table at the top shows a range of nutrients for a range of different products. In this case, four different um, uh, major meat commodities in the UK with seven different production systems. And each production system is assigned the amount of nutrients based on nutritional tables, national nutritional tables, and then they're compared to the recommended daily intake for each individual nutrient. And from there, a composite score is provided. The table at the bottom of your screen shows you the nutritional density score based on 10 encouraged nutrients minus 2 discouraged nutrients, in this case sodium and saturated fats. As you can see, the ruminant systems and particularly the beef systems have a very high nutritional density, whilst the sheep systems and the pork system have reasonably comparable nutritional density, whilst the chicken systems, both intensive and free range, have a low nutritional density. And this is not actually necessarily true. In fact, it demonstrates another methodological weakness in terms of data availability. And at the time that we published this study, we were unable to secure data for chicken which had the skin removed, whereas each other product was lean. So chicken in this particular study is being penalized for having the skin on. However, this is simply a methodological case exemplar and is not indicative of real-world scenarios. At this point, you may be asking yourself, where does this nutritional component fit into a carbon footprint or a wider environmental footprint analysis? Well, on the top of your screen, you can see how mass-based global warming potentials for all major meat commodities in the UK look. And this is taken directly from the science study published in 2018 that I mentioned at the beginning of my talk, but rather than representing the results as kg of protein, we changed the functional unit to 100 grams of meat. So the impact you're looking at here represent kilograms of CO2 equivalents per 100 grams of meat for each of the seven products shown on the horizontal axis. However, if we change that functional unit from 100 grams of meat to what percentage of your recommended daily intake does that 100 grams of meat produce in relation to 10 nutrients minus the two discouraged nutrients, then we see a very different picture. We see that the beef system, due to its high nutritional density, and in the case of the concentrate system, which has a very high efficiency of productivity, tends to have a lower carbon footprint than forage systems, we can see that the combination of high nutritional density and relatively lower carbon footprint actually means that it's comparable, if not lower, than the emissions from intensive pork production. Again, I'm going to stay away from chicken because in this study the results are slightly unreliable. But if we look at lamb, the nutritional density, whilst considerably high in lamb as it is in beef, the carbon footprint of lamb production from the study used in this example was too high to be offset by the gains in nutritional density. So essentially what we're looking at here are two ways of thinking about environmental footprints or carbon footprints. We can look at them on simply 100 grams of meat basis, or we can delve a bit deeper and think about, well, how much of that product do we need to eat to achieve our nutritional requirements? As you heard from Mel in the opening session, The majority of carbon footprints are usually calculated under IPCC's GWP 100 or Global Warming Potential 100. This impact assessment considers that methane is 28 times more damaging to climate change than carbon dioxide, whilst nitrous oxide is 265 times more damaging to climate change than carbon dioxide. However, there are newer approaches which allow us to disentangle the gases one by one and think about how changes over time can affect the climate dynamics. And in the next slide, I'm going to show how one of these approaches, notably GWP star, can affect our interpretation of a carbon footprint applied to a permanent pasture beef system on the Northwick Farm platform in southwest England. By using GWP star in addition to GWP 100 or GTP 100, we can explore the impacts of individual gases over time. We can see from the graph on the left that methane has a relatively high impact over the first 20 years, at which point it breaks down into carbon dioxide and water vapor, and the global warming impact becomes lower from year 20 to year 100. However, the long-lived cumulative gases, nitrous oxide and carbon dioxide, maintain the cumulative effect from year 0 to 100. When we combine the gases together to get a total footprint, we can see again that in the first 20 years the footprint is quite a bit higher. This is due to the short-lived impact of methane, and once methane breaks down, we can see the total carbon footprint drops, but this is driven largely by carbon dioxide and nitrous oxide from years 20 to 100. Nutritional carbon footprinting is rapidly becoming a go-to standard for the LCA community interested in producing results for multiple stakeholders of agri-food supply chains. And this is simply because it produces information on the flow of nutrients from farm through to retail through to the consumer, so there's information for everybody. There remains, however, a lack of notable standardization, which means it can, if not used transparently, become easy to draw desirable conclusions. There are many ongoing efforts amongst the LCA community, however, to make a more streamlined approach to nutritional LCA where certain sensitivity analysis or mathematical assessments need to be carried out before a study is considered robust enough to be published. Whilst functional units, as mentioned in the nutritional section, or scaling factors pose one problem, another problem within the carbon footprinting realm of science is to do with impact assessments. And I guess one of the most commonly known ones at the moment is Global Warming Potential 100 versus GWP star. Despite scientific disagreements on best practices, however, there is unanimous agreement amongst credible researchers that there remains a great deal of work to achieve net zero greenhouse gas emissions across all economic sectors, not just agriculture. Thanks everybody for listening. If you are interested in the farm data underpinning the GWP star component of this study, then please see the website at the bottom of this screen. Many thanks for your attention.